In the previous video, we took a look at an experiment known as the Michelson-Morley Experiment, which showed that all observers, no matter how fast they are moving with respect to each other, always measure the exact same speed for any bit of light that they're looking at. Now, this is going to force us to have a big rethink about a lot of our thoughts about the Galilean transformation. And we'll start with the first big rethink we're going to have, and that is the notion of simultaneity. So we'll just start with this classic thought experiment. Let's imagine that I'm standing on a train car, like so, and you're standing on the tracks by the side. So now you'll see me moving to the right with velocity v. So since you're pretty much the narrator in this problem, that's going to make you the unprimed observer, so we'll call you O. And since I'm the one that the narrator seems to think is moving, I'll be called O prime here. Now, when you're watching this happen, you observe the most amazing thing. In fact, actually you see it, because at the exact instant that the center of the train car passed you, you saw lightning flashes strike the front and back of the train car. And so you can observe that these must have happened simultaneously or at the same time, because you're equidistant from both flashes. So you know light took the same amount of time to travel from A to you and B to you. So you conclude then that the two lightning bolts struck at the same time. Well, what am I going to observe? What I'm going to observe, and we'll go ahead and say that my name for the event of the lightning flashing the front of the train car we'll call B prime. For the back of the train car we'll call it A prime, just to keep them straight. So you say that A and B happened at the same time. What do I say? I'm actually going to say that the lightning bolt that struck the front, B prime, happened before the lightning bolt that struck the back of the train, A prime. And you would say, well, how could you possibly say that that makes any sense? Well, let's think about it just for a second from your perspective. From your perspective, I'm moving to the right? So this means that from your perspective, I am seeing the light from B first because I'm running toward it. I'm running away from the light at A, and so you would rightly conclude that I would see B prime before A prime. But keep in mind that since I'm an inertial observer, I'm allowed to say that I'm stationary and that you're the one who's really moving, in this case the other way. So what do I see? Well, here I am at the midpoint here, and we both agree that I saw B prime first and then A prime. So we'll say second. And again, I am equidistant between the points. So I would conclude that the light took the same amount of time to travel from here. So I see this light flash first, and then I see this light flash later. But since I know these distances are the same, I conclude that B happened before A. B prime happened before A prime. But I need to be able to explain why you saw it the other way. In my frame of reference here, so this is how I'm seeing it, I see you, so let me just label myself here again, O prime. So I see you, O, moving to the left at V. And what I would say happened is that you were running away fast enough that the light had to travel from some extra distance from B to get to you. And then eventually caught up with you when you got here. Meanwhile, since you were running towards A, that light didn't have to travel as far. And it just so happened to work out, I would conclude, that although B had a head start, the fact that you're running away from B was perfectly canceled out, and so the two flashes of light got to your eyes at the same time. So the question is, who's right? So pause the video and get back with me. Okay, so the answer is we're both right. What is happening here is we are having different experiences of space and time. But it has to be this way if the experimentally confirmed fact that we both measure the same speed of light is true. We have to disagree that if two things happened at the same time in your frame, then that means that they did not happen at the same time in my frame, and vice versa. Now, if it makes you feel any better, it has been demonstrated that if there could even potentially be a cause and effect relationship between two events, if one event could possibly cause the other event to happen or could influence that event or whatever, all observers will agree that a cause kind of event will happen before the effect kind of event. They will disagree about how much time passed between the events, but they will agree that the cause happened before the effect. So it's not like it's totally crazy go nuts. But here, with these two events, there was no way they could have influenced each other. For this one to influence this one, the information about this event would have to travel at the speed of light to get over here, while this was already happening. So these two events didn't have any influence over each other. And so for events like this, where there can't possibly be any cause and effect relationship between the two, there will be one observer who says it happened at the same time. There will be a whole bunch of observers that say that B happened before A, like me. And there will be even other observers who say some observer who is moving to the left with respect to you would say that A happened before B. And we would all be correct. It's not an illusion or an appears to be or something like that. We are having different experiences of space and time. Now, we can take a look at what happened in our frame and figure out what somebody else would observe. So, although we're having different experiences, we can tell what those experiences are. Now, something to note here. This is going to matter for things like measuring lengths. Because remember, in an earlier video, we were saying in order to measure the length of something, I need to have two events happen at the same time. So if I'm going to measure the length of, say, this very train car, you could use the events of the two lightning bolts hitting the train car to locate the x-coordinates of the front and the back of the train car and figure out the length. I can't use those two events because for me, they didn't happen at the same time. So if I was to subtract the distance between the events, I wouldn't get the length of the train car. So this means that we're going to have some disagreement about the lengths of things. And we're also going to have some disagreement about how much time elapsed between things. So let's start with the time side of it, because it's probably the more straightforward. So the phenomenon is called time dilation. And it's due to, again, this is coming from a thought experiment due to Einstein. A thought experiment is just a tool that theoreticians use to imagine, to guide their theoretical explorations. So they imagine doing an experiment without actually physically doing one. So this is a thought experiment due to Einstein. He's trying to get down to the nuts and bolts of what makes up a clock. And he realizes that because if you remember all the way back to mechanics, we said a clock, time is that thing measured by a clock. So now that we're having a bit of a crisis about what is space and what is time here, we need to think really hard about the clock. So Einstein came to the conclusion that in order for something to be a clock, it needs to have a reliable tick and tock. So he then got to thinking, what would be like the one clock that absolutely everybody would agree works the same way? Well, it would be one that somehow involved the speed of light. So what he imagines is a photon of light going from one mirror to the other. So this is the tick. And then when it bounces back, that's going to make our tock. So this is called a light clock. Now here, if you are in the frame where an object is seen as not moving, you are said to be in that object's proper frame. So we can figure out the time that elapses between a complete tick-tock cycle. We'll call that time delta tau, because again here, in order for us to measure the length of something, we had to have two events that happen at the same time. In order for us to measure the time, proper time, we're going to have two events that happen in the same place. So we go from tick back to tock. So the light will have traveled a round trip distance of 2d at a speed of the speed of light. Now this is a delta tau, which is a pretty standard notation for what's called the proper time interval. That's the time between the two events in the frame where the thing is seen as not moving. I will just rearrange this real quick because it'll be helpful for me, and I will observe that we can write this d as c delta tau over 2. Just hold that thought for a moment. All right, so now let's go into what's called the dilated frame of our light clock. So when you are in a dilated frame, the thing is seen as moving. So here we're in a dilated frame. And I'm just going to grab kind of snapshots of our light clock. Probably need to goose that over just a little to the left. There we go. At 3 spots. So we'll start at the beginning of the tick, the end of the tick, / beginning of the tock, and then the end of the tock. So if we follow, in a frame where our light clock is seen as moving here to the right with velocity v, we'll still agree that this distance here is d. But now, when we watch the tick happen, the photon isn't going straight up and down anymore. It's like the analogy I was making in an earlier video about Tony Hawk and the skateboard. We will see the tick doing that, and the talk, I can draw better than that, maybe. So, yeah, well, I tried. The tick will look something like that, and these should be the same angle. I'm not the best artist. And the talk should look like that. So how far did the light... Now, it turns out that for this exact configuration, we can just focus on the tick. In general, you have to worry about both the tick and the talk because of the whole symmetry of the thing. But here we can just focus on the tick. So how far did this move from tick to talk? From the beginning of the tick to the beginning of the talk? Well, this will be v times, now I'll call this delta t over 2. Because here I'm going to say that the time elapsed, delta t, in this dilated frame is going to be equal to, well, what? 2 times this distance here over c. So we need to figure out what that distance is. So this distance here, this light is traveling at the speed of light. The time it took was, let me back up. So let's focus for just a moment on this triangle here. So this here is the path that the light took on the tick. It's going to travel c delta t over 2. This horizontal leg we worked out was v delta t over 2. And then this vertical bit here is just our friend d, which we cryptically had expressed as c delta tau over 2. So now we can use the Pythagorean theorem here. We can get that this length here is going to be c delta t over 2 squared. And that'll be equal to v delta t over 2 squared plus c delta tau over 2 squared. All right, let's just square everything. So this is going to give me c squared delta t squared over 4 is equal to v squared delta t squared over 4 plus c squared delta tau squared over 4. And we will have a cancel-palooza of the force. So the goal now is to try to express delta t in terms of delta tau, the time elapsed in the proper frame. So let's just go ahead and rearrange this. So if I subtract this from both sides, I can pull out delta t squared, so I'll get, I will get c squared minus v squared delta t squared. That's equal to c squared delta tau squared. So then I can rearrange this some more to get delta t squared is c squared over c squared minus v squared. I'm going to leave a little space right here, delta tau squared. Now to get this into a more standard form, because in relativity it makes sense to measure all of our speeds with respect to the speed of light, what I'm going to do is I'm going to multiply numerator and denominator by 1 over c squared, like that. So doing that, I will get delta t, delta t squared to be 1 over the 1 minus v over c squared delta tau squared. Now all that's left is to take the square root of both sides. So we will be left with delta t is equal to 1 over the square root of 1 minus v over c squared delta tau. Now, at this point, I want to introduce some notation. This notation is super duper standard in the world of relativity. Most of us will define a constant beta to be equal to v over c. So this is just saying how fast as a percent of the speed of light is something going. So this doesn't have any dimensions, it's just a percent of the speed of light. So then that will, we can then write this as delta t is 1 over the square root of 1 minus beta squared delta tau. And then it turns out that this combination here, this 1 over the square root of 1 minus beta squared, shows up so much that we give it its own name too. We define this to be lowercase gamma. So usually we will just write then that delta t, or the time between between two events in the dilated frame, is equal to gamma delta tau. And this is with gamma being 1 over root 1 minus beta squared, and beta being v over c. So in practice, what will happen is as soon as you see relativity start coming around, a physicist's reflex is just to immediately calculate beta and calculate gamma because they know that they're almost certainly going to need them. Now, it's going to take us a few videos to get there, but we will eventually show that nothing can go faster than the speed of light. So this constrains beta to run between 0 up to 1. And if beta is 0, that makes gamma 1. And as beta approaches 1, gamma approaches infinity. So gamma is always going to be a number bigger than 1 as long as something's moving. So what does this mean? This means that in any frame where something is seen as moving, the time between two events is longer than in a frame where it is seen as stationary, because this is the proper time interval, so this is where it's stationary. This is the dilated time interval. This is seen where it's moving. So this even corresponds to things like, say, just the ticks on a watch. So the mnemonic that people use to help keep straight which is which is to say that moving clocks run slow. Now, that's a bit of a misnomer because in the frame of the clock, I mean, as long as the clock is built correctly, in the frame of the clock, the ticks and tocks are happening once every second. But if you see a clock moving, you'll notice that the display is updating more slowly than the display on, say, your own watch or something. Well, if you had super duper amazing bionic eyes or whatever. So in practice, so if, say, someone is running past you, in principle, you could look at their watch and notice that their watch was running a little more slowly than yours. And you would be right. Now, in practice, for any speed, because the speed of light is 3 times 10 to the 8 meters per second. If you're talking just a few meters per second here, these factors of gamma are like literally 1.8 and about 9 zeros or 10 zeros and a 1. So you're not going to notice this comparing wristwatches with each other. However, an experiment was done to test this, where a pair of very accurate atomic clocks were set up. One was left at an airport, while the other one was loaded into an aircraft and flown around the world for quite a while. And upon comparing the signals from the atomic clocks, yes, indeed, the atomic clock on the aircraft appeared to be running slow. Now, to the atomic clock on the aircraft, it was operating just fine. In fact, it was saying that since it saw the one on the runway as moving, that was the one running slow. We'll get into the resolution of how to tell who really aged less. That's called the paradox of the twins. That's coming up in another video. But it is true that if I walk past you and you look at my watch ticking, you'd say my watch is ticking slow. Again, keep in mind, I'm entitled to be an inertial observer. I can say, no, you're really moving past me. And when I watch your clock tick, it's running slow. And we are both correct. Now, like I said, there are paradoxes associated with this, which is known as the twins paradox, and we'll resolve this. But I want to be very clear that this is not just some sort of optical illusion or it's some weird force that's making clocks run slow or something like that. It's not. We are having literally a different experience of space and time. So this means it isn't just confined to clocks. Anything that we could use to mark the passage of time is similarly influenced. For instance, atomic processes, the rate at which an electron orbits an atom, is a perfectly good clock. And if that atom is seen as moving, you'll observe that electron is moving more slowly. Well, then that's going to have influences on things like, say, collections of atoms formed into molecules that eventually are formed into biological organisms. That's going to have a say on their aging. So yes, if you see something moving past you at a substantial fraction of the speed of light, you will notice them aging more slowly than you. Now, they won't notice any difference. They will just say, yeah, I'm aging at 1 year per year, like we all do. But their experience of the year is different. Now, for this to really show up in any noticeable amount, you've got to be moving at a substantial fraction of the speed of light. So let's just go and take a look at a case here. Let's say we've got a person here who is looking at their shiny wristwatch. There we go. That's supposed to be their watch. Oh, well, I tried really hard. The ticks on the watch will happen once every second, so that would give us a proper time interval between watch ticks of 1 second. Now you're going to say, you're going to say though that you see them as moving at 0.9 c. So what you want to know, so here you are watching them, is what time will you measure between the ticks of the clock? So the usual rule of thumb here is as soon as you see relativity happen, calculate beta. Okay, step 1. Beta is V over C. V here is 0.9 C over C, so beta is just plain 0.9. All right. And then you also calculate gamma. Gamma is 1 over the square root of 1 minus beta squared. So this will be 1 over the square root of 1 minus 0.9 squared, which is 2.29. So now using your mnemonic of moving clocks run slow, really the way most physicists do this is they then say to themselves, all right, do I multiply or divide by gamma? So since you would see the events of the ticks of the watch happening more slowly than the owner of the watch, you would say that more time elapsed. So that does indeed assure us that yes, the watch is the proper frame here, and then you looking at the watch move, that's going to be the dilated frame. So delta t equals gamma delta tau. So this will be 2.29 times the 1 second between ticks, or 2.29 seconds. And yes, experiments have been done at these kinds of speeds and even higher, and this sort of thing does indeed show up. But again, in our everyday life, beta is going to be a number that's something like a whole bunch of zeros and a 1. And then you're going to square a whole bunch of zeros and a 1, subtract it from 1, take the square root. You're going to get a number that's just barely bigger than 1. So in our everyday life, although these things are happening all the time, you don't notice them because the difference is so small. All right, so the related phenomenon to time dilation is length contraction. Because remember, since we had to give up on simultaneity, that means that not only do we disagree on how long the time interval is between two events, we also have to disagree about the distance between two events. This phenomenon gets called length contraction. So if we go back to our train car here. So here I am sitting on my train car. And we'll have you over here by the side of the tracks. So we'll say that to mark our two events, we will think about an orange pylon that happens to be sitting next to the side of the tracks like so. Now, so the two events that we're going to use are orange pylon meets front of train car and orange pylon meets back of train car. So if I calculate my speed, I'm going to say that it is my proper length. So we'll say the length of this train car is L. This gets called the proper length, because this is what I measured the length of the train car to be in a frame where it's seen as not moving, because I'm stationary with respect to the train car. I'm seeing the pylon move from here to here. Since those two events are not in the same location, the time that I measure between them is a dilated time, delta t. Similarly, you'll go ahead and do the same kind of calculation. You'll say that the speed of the train car, I was saying it's the speed of the pylon. For you, it's the speed of the train car. Well, that's easy to measure. We take the distance that we'll take the length that we see the train car to be. We'll call that counterintuitively capital L, even though it's going to turn out to be smaller. This is the dilated length, because you're seeing my train car is moving. D-I-L-A-T-E-D, length. But the two events of front train car meets pylon and back train car meets pylon happen in the same location. So that is a proper time. All right. So we both have to agree. You have to agree that my train car is moving to the right at V, I have to agree that the pylon is moving to the left at v. So we can go ahead and equate those two here. So we'll have L over delta tau is equal to the proper length over delta t. So we can then remember from time dilation that delta t was gamma delta tau. So if I cancel the delta taus from both sides, I get that the dilated length is the proper length over gamma. And this will always be less than the proper length. So the mnemonic that people use for that is that moving meter sticks are shorter. Again, in the frame of the meter stick, a meter stick is 1 meter long, period. But you and I are having different experiences of space. And so, while I will have measured the distance that the pylon traveled from front to back to be the proper length of the train car, L, you're going to say that the train car was shorter. But you're going to say the train car is shorter, but you're also going to say that it took less time to go past the pylon. That's how we're both going to agree on the same speed and keep that consistent. Now, it's important here to know, too, that the contraction only happens in the direction of motion. So if we think about observing, say, a cube, and I'm being careful here to say observe. If I think about some cube moving to the right at ridiculous speeds, what you would observe, so if you collect together all the reports from all the really small people in the latticework of clocks, asking them, hey, was there a cube right there when you were there? What you'll see is that these dimensions here, the vertical, the front and back dimensions, the side to side and the end of the screen dimensions are the same, but that it's squished in the direction of motion. That's what you would observe. Now keep in mind with what you actually see, when you're going this fast, how the light would hit your retina. The light from here had to have traveled from longer, so it would have been had to come from an earlier time, which means that the whole thing would be moved over to the left a bit. So what you would actually see is it's going to be some really kind of twisted, distorted mess where the back part is off to the left more than the front part. Okay, something like this. This would be what you would see. But even here, as you watch this thing go by you, you can start to calculate out where and when all of the different bits of light originated from, so that you could eventually compute that although you see something incredibly distorted like this, it actually is looking like this in 3D. So, as some experimental confirmation that length contraction is indeed actually happening, I will point out that this helps to resolve a problem about particles coming in from the upper atmosphere called muons. So, for our purposes, the muons get made about 10 kilometers or so above the surface of the Earth. And a cosmic ray, which is really a particle, but the name stuck. This is particles are typically like ejected at ultra-relativistic speeds from, massive stellar events. Every so often, one of these cosmic rays coming in from some massive stellar event many light years from here just happens to strike the upper part of our atmosphere. And actually, this sort of thing happens all the time. And when it interacts with the molecules in the upper atmosphere, it's likely to make a muon. Now, these muons will come out at a variety of speeds. Oops. But let's just look at the population of muons. They're all moving very, very fast, very relativistic. So let's look at one that's going at 99.8% of the speed of light. Now, these subatomic particles, a muon is actually a particle that's like an electron, but a couple thousand times heavier. So it's like an electron, but it actually has closer to the mass of a proton. If you just have a muon just sitting there all by itself in the lab, or actually a collection of them, you'll notice that half the sample of muons will decay in 1.5 microseconds. Now, if you're going at around this kind of speed, you're probably going to need the muon to live a little longer than that. So what happens is, this is what's called the half-life. So it means in 1.5 microseconds, you're down to half the number of muons you made. In 2 half-lives, or 3 microseconds, you're down to a quarter. In 4 half-lives, or 4.5 microseconds, you'll be down to an eighth, and so forth. So if you do the math in between this, you get that the percentage of muons that live for at least 2.2 microseconds is about 36%. Now, if relativity weren't a thing, and you were to calculate how long it would take for this muon to travel 10 kilometers, you would see that it would be so many half-lives that we should never detect a muon on the surface of the Earth. Because it would basically, for all practical purposes, almost all of them would have decayed. But here's where time from our perspective, time dilation comes to our rescue. If we go ahead and calculate beta and calculate gamma here, so beta is going to be 0.998 c over c, so 0.998. Gamma will be 1 over the square root of 1 minus beta squared. So gamma is 1 over the square root of 1 minus 0.998 squared, which when you crunch that through is about 15.8. So this means that our 2.2 microseconds that we need basically for the muon to make it to the surface of the Earth, this means our 2.2 microseconds in the lab frame would be gamma times the 2.2 microseconds the time that we measure it taking will be gamma times the time you'd measure our 2.2 microseconds. So this would be 15.8 times 2.2 microseconds. We get 34.8 microseconds. Now it turns out that 34.8 microseconds is going to be roughly the time it takes for muons here to make it down to the surface of the Earth. So instead of it being over 20 half-lives, which means that we would basically never see any of them, we see about a third of them. All right, but how do we explain this from the perspective of the muon? So, from the perspective of the muon here, remember the muon is just going to say, hey, I came into existence right here, right when the upper part of the Earth's atmosphere collided with me. Now what I'm going to see is the Earth's atmosphere moving up to me and then eventually a detector hitting me. But I am seeing the Earth move up at 0.998 C. So if this distance here, the proper length is 10 kilometers. Let's see what that works out to be in the muons frame. So this dilated length is going to be the proper length over gamma. So the proper length was 10,000 meters. Gamma is 15.8 meters, or sorry, 15.8 to give us 632 meters. So to the muon, the Earth's atmosphere is only 632 meters thick. You know, a handful of soccer fields. And that's plenty short enough that for an Earth moving at 0.998 C, it can cover that 632 meters in the 2.2 microseconds now that matter in the muons frame. So we both agree that about a third of the detectors the muons hit the surface of the detector and surface of the Earth. In the frame of the Earth, we explained this by saying that the muon is moving so fast that its experience of time is much slower than our experience of time. So thus, despite the fact that we should normally never see any muons make it here, we see about a third. From the perspective of the muons will conclude that the Earth is, because the Earth is moving so fast, its experience of space is different than that of the muons. Its experience of space is so different than that of the muons that to the muon, the Earth's atmosphere is only 632 meters thick. And so in the 2.2 microseconds that it takes for us to be down to about a third of the muons left, the Earth has actually moved 632 meters, and so the detector can collide with the muon and be detected. So it's a combination. In the one perspective, it's the difference in the experience of time that matters. In the other, it is the experience of space. Now, I did promise that there is still the issue to think about when I said that when we see watch each other's watches, we each see each other's watches as moving slowly. That's a thing called the twins paradox, and I'm going to address that in the next video. So catch you over there.